Okay, so the question is, can the function sine of t squared be a solution on an interval containing 0 of linear homogeneous differential equation of second order with continuous coefficients? Well, I like this question because it has three completely different solutions. And usually, well, at least in my tutorial group, so different teams invented all the three solutions. So let me share all the three solutions with you. So solution one. So solution one basically follows the same logic as in question one, right? So the idea here is that since we apply the Wronskian in question one, so let us try applying the Wronskian in question two, right? So we know that y is sine of t squared. Well, but if this is a solution on an interval, blah, 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 of some differential equation, then there's going to be another solution, right? So let us denote this sine of t squared as y1, and let us introduce another solution that is linearly independent of y1, right? So this is another solution, and suppose that it is linearly independent of y1. Well, but then in that case, the Wronskian of y1 and y2 should not be 0. So the Wronskian of y1 and y2 should not be 0, evaluated at any point. And of course, since we are talking about an interval containing the point 0, then we probably should try 0. So at the same time, so let us compute the Wronskian. So now y1 is sine of t squared. y1 prime is what? We need to differentiate sine of t squared. So the derivative of sine of t squared is 2t times cosine of t squared. So here we're going to have y1 and y2 and y2 prime. Y2 prime. So evaluated at 0. So when letting t be 0, the first column of the Wronskian is going to be 0. Well, which means that regardless of y2, the whole determinant is 0. So this contradiction concludes the proof. Okay, now what is this is kind of a way to solve it, just based on the idea that, we just saw Wronskian, and then why don't we try to apply it again? So the second way to solve it is sort of straightforward, or I don't know, sort of brute force way to do it. So suppose that this is indeed a solution. So let us just, compute. This is if y is sine of t squared, then y prime is, we've just computed it, is 2t times cosine of t squared. Well, so let us just compute y double prime and plug it into the equation, right? So y double prime, we've got to differentiate y prime according to the product rule. First we differentiate t, so we get 2 times cosine of t squared plus 2t times the derivative of cosine of 2t squared. So it's going to be 2t times minus sine of 2t. So it's going to be minus 2t times sine of t squared. Well, but then let us just plug it into the equation, right? So as y prime, y and y double prime. So plug it into the equation. We're going to get the following formula. So 2 cosine t squared minus 4t squared sine t squared plus p of t times y prime 2t cosine t squared plus q of t times y times 2t cosine of t squared equals 0. Well, of course, it kind of seems that the left-hand side is not really 0, and the right-hand side is 0, but we need to carefully prove it, that it is impossible for the left-hand side to actually be 0. And notice that here we have, p of t, which can be anything really, q of t that again, can really be anything. So we need to make sure that it is impossible to find P of t and Q of t such that the left-hand side becomes 0. Well, and I guess the idea is that since, everything happens in a neighborhood of 0, so we'll just try to let t be 0 and substitute it into this equation. And letting t be 0, we will get 2 equals 0. So the left-hand side becomes 2 and the right-hand side becomes 0, which is a contradiction. So it concludes the proof using the second method. Okay, so the second method is sort of kind of straightforward method. But also at the same time, there is the third method that I guess is the shortest, but in my experience, students sort of probably is the rarest that students invent. So the shortest method, in my opinion, is as follows, right? So if y equals sine of t squared is a solution of the given differential equation, then notice that y of 0 equals y prime of 0 equals 0. And so it means that this function sine of t squared satisfies the initial condition y of 0 equals y prime of 0 equals 0. But also notice that the constant 0 is also a solution of the given differential equation, and it also satisfies the same initial condition. So which is a contradiction to the Picard-Lindelöf theorem, according to which there may be just a unique solution of the given initial value problem, right? So here, assuming that sine of t squared is a solution, we found another solution, and therefore we find at least two solutions which violates the uniqueness of solutions of any initial value problem. And since uniqueness is violated, it means that it contradicts the Picard-Lindelöf theorem, and that's a contradiction. All right, so this is all I wanted to share with you regarding question 2. 3 different solutions. All of them use kind of different statements from the course, which is why I like this problem very much.